this video, we're going to go through the Grignard addition to esters, as well as hydride reduction with LiAlH4 with esters. And then we'll also throw in the mechanisms for hydride reduction of carboxylic acids and amides. Let's get into it. All right, when you react an ester with a Grignard reagent, we're going to have two successive additions of our Grignard reagent into the structure. That's going to net result produce a tertiary alcohol product. So we'll slice and dice, reacting the carbonyl twice. Now, mechanistically, the Grignard hella nucleophilic. That's going to attack right away, breaking the pi bond. In the first tetrahedral structure, there's only one leaving group, and that would be the OR minus leaving group of our ester. So we attack, collapse, kicking out that OR minus leaving group. In the workup step, that will eventually become the alcohol byproduct. Notice that's producing a ketone intermediate. Now, even if we wanted to stop here, we can't for two reasons. The ketone is more reactive than the starting ester, and ketones are compatible with Grignard reagents. So that ketone intermediate that we generate will continue to react. We have a second Grignard add into the structure. And at that point, there's no more leaving groups. I've just got carbon attachments here, no more leaving groups. So I'm going to do my second step, my acid workup step, and protonate that O- charge to complete this synthetic sequence and make my tertiary alcohol product. Now, this mechanism would be identical if you were to react your acid chloride with a Grignard. Two successive additions of the Grignard would also occur with your acid chlorides. To recap that really quickly, we attacked right away, broke the pi bond. There was only one possible leaving group, the OR component of our ester. We'll collapse and kick that out, forming a ketone intermediate. That ketone will then continue to react. We have a second Grignard reagent add in, producing a tetrahedral structure with no more leaving groups. Therefore, we would do our H3O plus workup step, protonating the O- charge to form a tertiary alcohol. Now consider with me really quickly here, what would happen if we reacted a Grignard with a carboxylic acid? Instead of reacting at the carbonyl carbon, generating a new carbon-carbon bond, the Grignard carbon just acts as a strong base and deprotonates the carboxylic acid. That is a classic case of quenching. Get a quench. No new carbon-carbon bond is formed. We just deprotonate the carboxylic acid. All right. So now let's consider hydride reduction of your ester. The ester, being a lower reactive derivative, cannot reduce with NaBH4. I would have to use lithium aluminum hydride specifically to reduce that. With the ester, visually, we're going to slice and dice, and we're going to hit the carbonyl twice. We're going to have a 2 times reduction, producing a primary alcohol. Let's track that together. LiAlH4, very strong nucleophile. We're going to attack the carbonyl carbon, break the pi bond, generate the first tetrahedral structure. There's only one possible leaving group, and that is the OR minus leaving group. So we'll collapse and kick that out. After the workup, that becomes the alcohol byproduct. That produces an aldehyde intermediate, and even if we wanted to stop there, we can't. Okay, for 2 reasons. The aldehyde is more reactive than the starting ester, and the aldehyde itself has compatibility with lithium aluminum hydride. So we can't stop there. LiAlH4 will produce that carbonyl. That's our second hydride adding in. And after we break the pi bond of the aldehyde, adding in our second hydride, there's no more leaving groups. So we perform our H3O plus workup step, protonating that O- charge, and we get a primary alcohol product. So we slice and dice, add twice. All right. Notice that's conceptually identical to the mechanism of ester plus Grignard. Conceptually identical. We're just using, with a Grignard, a carbon nucleophile, and with LiAlH4, we're using a hydride nucleophile. Okay. Now, acid chlorides would also reduce by that exact same mechanism, but the acid chloride could be reduced by both NaBH4 and LiAlH4. Now, I've just drawn this in here, and you can, pause the screen if you want to draw this out yourself and then follow along, or you can just watch for now. when you reduce the carboxylic acid with LiAlH4, I'm going to advocate for just, if we're predicting the product alone, a visual erasure strategy. That is to say, if you just erase the carbonyl and imagine adding 2 hydrides to that carbon, that's the visual of your product. We produce a primary alcohol product, and we can use a visual erasure strategy. With the ester, with LiAlH4, we needed to slice and dice because it was important to track that alcohol byproduct. But with the carboxylic acid, I can use this visual erasure strategy. Now, the mechanism for hydride reduction of your carboxylic acid is a little bit different from that of hydride reduction of the ester. And that's because of this acidic proton in the carboxylic acid. Lithium aluminum hydride, don't forget, is a very strong base. So what's going to happen here first is we will deprotonate the carboxylic acid. The hydride grabs that hydrogen, producing hydrogen gas that escapes the mixture. That produces a carboxylate ion. That carboxylate ion will then complex with the aluminum, and that charges the aluminum negatively. From there, we're going to have an intramolecular hydride addition. That is to say, we added a hydride breaking the pi bond of the carbonyl. In that tetrahedral structure, the only appropriate leaving group is our oxygen attached to the aluminum. So we will collapse and kick that out. That produces an aldehyde intermediate, which of course is going to continue to react. It still has compatibility with LiAlH4. We attack the aldehyde. After that second hydride addition, there's no more leaving groups. Therefore, we will just protonate that O- charge in our H3O+ workup step. That result forming a primary alcohol. And to reiterate, with the carboxylic acid and lithium aluminum hydride, you can just use a visual erasure strategy if you just want to quickly predict the product. Now, let's imagine reducing the amide. The amide, also being a lower energy derivative, also needs to reduce with LiAlH4. And with the amide, you can also use your visual erasure strategy. If you just erase the carbonyl, imagine a 2 times addition of hydride to that carbon. That's more or less what your product looks like. Now, a couple things here. We're going to use the visual erasure strategy specifically here, and I really want to accentuate that because we are not slicing and dicing. Notice how that carbon and nitrogen maintain their attachment point. Let's track the mechanism, see how that plays out. Mechanistically, lithium aluminum hydride, being the good nucleophile that it is, will attack and break the pi bond right away. Then, instead of collapsing and kicking out a nitrogen of negative charge, which of course is a very strong base and a bad leaving group, we're going to have the O- complex with the aluminum. Then the nitrogen is going to pull a Uno reverse, switcheroo. Uno reverse, the nitrogen is actually going to collapse and kick the oxygen out. That forms an iminium-ion intermediate. That iminium-ion intermediate is then going to be susceptible to hydride reduction. LiAlH4 reduces the iminium-ion intermediate, and that produces your amine product. Okay, so we do not slice and dice. We do not slice and dice because the nitrogen actually pulls the Uno reverse, kicking out the oxygen atom. All right. So this video has been Grignard addition and hydride reduction. Grignard addition and hydride reduction to the ester, mechanistically pretty much identical, but the hydride reduction mechanism for carboxylic acids with LiAlH4 and amides with LiAlH4 proceeds slightly differently.